To educate yourself is your responsibility. To get knowledge is your duty. And until you understand the importance of gathering a lot of knowledge, you will not take it very seriously. But when you do, you realize that you don't have enough time. You don't have much time to get all the knowledge you need. And so you have to work on it. This topic here is a topic you really need to understand in IT. No matter what, you need to get a hold of this. If you can get a hold of this topic, IT will be easy for you, and vice versa. So I want to take my time and teach it very well. So once again, I welcome you to our class on the binary number system. This is lesson 5 in our level 1 IT training. So we are still talking about the binary number system, and the last time we started with the definition, and we said binary is a base 2 number system, and it is made up of only 2 digits, which are 0 and 1. We also learned that binary is the most basic language in computing. It's the most basic language of computers. As a matter of fact, computers only understand binary. Computers don't understand any other language apart from binary. Any other programming language out there will be converted into binary before the computer will operate on it. If you hear of any programming language like Java, C++, Ruby, Python, PHP, those are called high-level programming languages. And when any code is written in those languages, those codes are compiled or translated back into binary before they will work. And so binary is still the only language of computers. We also learned about bits and bytes, and we said bits stands for binary digit, and bytes represent 8 bits. When 8 bits are put together, we get what is called a byte. We said a 4 bit is called a nibble, and 8 bits is called a byte. We learned that computers operate in chunks of 8 bits, and so when data is being stored, we address the data as bytes. When data is being stored, we don't address the data as bits, we address the data as bytes. The reason is that when keyboard characters were being invented, it took 8 bits to be able to represent each keyboard character in human language or in human text. So the text you see on your screen, for the computer to come up with such a text or a letter, for any letter to show on your screen, for the computer to compose that letter, it will use 8 bits. And so what was standardized was that 8 bits will be used to represent every keyboard character. So every keyboard character occupies 1 byte, and 1 byte is the same as 8 bits. If you open to any plain text editor and you type some text, the system will count each letter and will determine the total size of the file you will create with that text editor. So if there are 2,000 letters, I'm not talking about 2,000 words, 2,000 letters, it will occupy 2,000 bytes because each letter occupies 1 byte. And we learned that 2,000 bytes is equivalent to 2 kilobytes, because 1,000 bytes is the same as what? 1 kilobyte. As a matter of fact, if you want to be very, very technical, it is 1,024, but we just round it to 1,000. So 1,024 bytes will give you 1 KB. All right. So we said that 1,000 bytes will give you 1 kilobyte, 1,000 kilobytes will give you 1 megabyte, 1,000 megabytes will give you 1 gigabyte, 1,000 gigabytes will give you 1 terabyte, and 1,000 terabytes will give you what? 1 petabyte. 1,000 petabytes will give you 1 exabyte, 1,000 exabytes will give you 1 zettabyte, and 1,000 zettabytes will give you 1 yottabyte. A day may come when we'll be dealing in yottabytes. Today, we are mostly operating under petabytes. All right. We also talked about other number systems used in IT, and we introduced you to the octal number system, which is base 8, the decimal number system base 10, and the hexadecimal number system base 16. All right. Today we'll continue and delve a little bit into the relationship between binary and decimal. Because we humans are educated or trained in decimal, computers work in binary. And so because we are working with computers, we'll be interchanging, or we'll be working between decimal and binary. Because humans speak decimal, computers speak binary. So how can they communicate? So we'll look at some relationship between decimal and binary. All right. I want to play a very short clip to prepare you for what we are about to discuss.
Welcome to this presentation about the language of computers. The first thing to know is that in the most fundamental sense, computers really only understand two things, on and off, which in computer language are represented by the numbers 1 and 0. This language, made up of just ones and zeros, is called binary. To better understand binary, let's take a quick look at the number system we humans use most of the time, the decimal system. The decimal system is a base 10 number system. We use the decimal system because humans have 10 fingers, so it makes sense to us to count in groups of 10. With the decimal system, we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once we get to 9, we've run out of numbers, so we have to add another digit. So we make 1, 0 to make 10. Then we get 11, 12, 13, 14, 15, etc., all the way to 99, and then we have to add another digit to make 100. Binary works in a similar way, except since we only have two numbers, 0 and 1, we have to use a whole lot more of them. Here's how it works. We start with 0, then 1. Now we've run out of options, so we have to use another digit. We get 1, 0, 1, 1. Now we've run out of possibilities again, so we have to use another digit. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now we've run out of options again, so we have to add another digit. We get 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. You get the idea. So why are we talking about this at all? Are you ever going to have to convert from binary to decimal or vice versa?
So we are now getting into real IT. Right now, your job is to know how to represent every decimal number in binary. Now, if you are dealing with decimal number 0, it is the same as 0 in binary. 1 is the same as 1 in binary. But 2 is not the same. 2 will be written as what? 1, 0. 3 will be written as 1, 0, 0. Is that what you said? You don't even know what you are saying. Let me open to Notepad and let's put them here. Okay, so we have decimal and we have binary. We said 0 is the same as 0 in binary, 1 in decimal is the same as 1, but 2 is what? 1 0. 3 is what? Why 1 1? Okay, let me just write it. It's correct. 4 is what? 1 0 0. Okay. So I'll be calling you to come on the board and I'll give you a number and you write it in binary. 5 is what? 1 0 1. Correct. 6 is what? 1 1 0. 7 is what? 1 1 1. Okay. 8 is what?
1 0 0 1.
Huh? 8 is 1 0 0 0. And 9 is what? 10 is what? 1 0 1 0. 11 is what?
1 0 1.
12 is what? 1 1 1 0. No. No, it's 1 1 0 0. 12 is 1 1 0 0. 13 is what? 1 1 0 1. 14 is what? 1 1 1 1 0. And 15 is what? All right. So the way you have gotten it very well right now. What I want, you see in the book, I've even written plenty. Okay, I'll give you up to 20. Okay, so your job is to write up to 25 for me. Right now, take a piece of paper on your exercise book and write from 0 to 25 in decimal, 0 to 25 in binary. Do that for me now. One of the tasks you'll be given is to learn how to convert from decimal to binary and from binary to decimal. So the numbers I gave you to convert, like 25, you are supposed to be able to convert it into binary. For you to be able to translate from binary to decimal or from decimal to binary, you can do that in several ways. One way is to study how the numbers are added and follow the pattern and make sure you don't miss anything. Let's use a formula to solve it. Converting from decimal to binary. Let's use a formula this time. To use a formula, for example, you've been given number what? 25, right? You need to write 25 and write remainder. And now you are going to do division. We call this a division method. Please, are you here? We call this a division method. Now, I'm not telling you to follow a pattern. To follow the pattern, you yourself can follow it with your own. You can use your own intelligence to follow it and get it. But now I'm going to give you a formula. And that formula always works. So if you are given a number like 25 and you are operating in base 2, this formula is called the division method. With the division method, you ask yourself, how many times will 2 go into 25? Who can answer that? How many times will 2 go into 25? 2 will go into 25 12 times, right? Because 2 times 12 is what? Would there be a remainder? Remainder what? You write the remainder. When you finish using the division method, the remainders will be your answer. So we are looking for the remainders. Okay, let's move to the next step. Now our number is 12. Our number is no longer 25. Our number is 12. How many times will 2 go into 12? 6 times. Would there be a remainder? If there's no remainder, you write 0, remainder 0. We are interested in the remainders. Okay, let's go ahead. Now, how many times would 2 go into 6? 3 times, right? Would there be a remainder? Remainder 0. How many times would 2 go into 3? 2 go into 3 1 time. Would there be a remainder? Remainder 1. Now, your last number here is 1. You can just bring the 1 down here or continue the calculation. How many times would 2 go into 1? It's going to 1 0 times, remainder what? Remainder 1. 2 will go into 1 0 times, remainder 1. You can do that, or you can end here and count from here. So when we are getting the answer, once you are done with the calculation, now we are done, you do your calculation till you get to 0. Your answer is being read from the bottom to the top. From the bottom to where? The top. So 25 in base 2 is equal to 11001. Whoever got it, this is the answer. 11001. Now, let's try and follow the pattern and show you. Maybe this will help someone. Watch this. Now we are using the pattern. Here we have 4 ones, right? So if we are asked to enter 16, because we have gotten to the end of 4 ones, we are going to increase by 1 with 4 zeros. This is what we are supposed to get, because we have gotten to the very end. So we need to increase by another set where we'll have 1 with 4 zeros. This is how the pattern has been. When we got to the end here with just 1, we increase to 1 with 1 0. When we got to the end here with 1 1, we increase to 1 with 2 zeros, right? When we got to the end here with 1 1 1, we increase to 1 with 3 zeros. Is that not what we did? So here, now that we've gotten to the end of 4 ones, we increase to 1 with 4 zeros. Is that not it? Now watch this. 17, because I know I have several zeros, I need to intelligently fill in the zeros. This is how you are supposed to do it. The next number is going to be 1 0 0 0 1. You have to start from the last one. Watch the next one. 18. 8 is going to be 1 0 0 1 0. Now your 1 will start moving to the left, but watch how it's going to be. 19 is going to be 1 0 0 1 1. There's 0 there, I need to fill it. Then 20 is going to be 1 0 1 0 0. You see, I'm just using a pattern. Then my 21 is going to be 1 0 1 0 1. Are you following? My 22 is going to be 1 0 1 1 0. My 23 is going to be 1 0 1 1 1. Easy. My 24 is going to be 1 1 0 0 0. And my 25 is going to be 1 1 0 0 1. Do you get it? Is it the same as the answer we got here? Okay, so I can use a pattern, or by the studies of the pattern, to get it. If you give me any binary number and you tell me to tell you the next number, I can give you the next number. Once I can get the next number all the time, I can keep on counting till I get to any value I want. So now when you are given this and you are told to find the next number, 26, you have to be able to solve this. Apart from learning any formula, you need to know how to add 1 to a binary code. So this is a binary code, 5-bit binary code. Add 1 to it. How are you going to do it? For me, because the last number is 1, my next number is going to be 1 1 0 1 0. This is going to be my next number. I always know how to add 1 to it. If it's like this, the next number will be very easy for you. Who can get it for me? 1 1 0. Excellent. You see that it was easy. The next one, who can get it for me? 1 1 1 0 0. So your job is to try and just add 1 to the next code, to the code given to you. Just add 1 to it. If you can solve that, you can solve any list given to you. Apart from that, okay, let's work it to 30. Watch this. So 29 is going to be what? 1 1 1. Excellent. Just need to know how to add 1 to it. Now 30 is going to be what? That's it. Okay, don't let it confuse you, because we are just trying to use our own brains to follow a pattern, so it may sound or look some way to you, but then we have formulas to easily calculate everything. One formula is what I've given you. Let's use the same formula to solve another number, 30. Let's convert 30 into base 2. To convert 30 into base 2, you ask yourself, how many times will 2 go into 30? Pardon? 15 times, remember. How many times will 2 go into 15? 7 times, remember. Is it correct? You can ask yourself, 2 times 7 is what? 14, so it's not up to, so remember 1. Okay, good. Now, how many times will 2 go into 7? 3, remember. How many times will 2 go into 3? 1, remember. How many times will 2 go into 1? 0, remember. 1. So what is your answer? 1 1. Excellent. Check what we did by the pattern. Is it the same? Is it the same? Good. So that is it. So solve the following numbers for me using the division method. So first of all, you solve 65. I've given you 4 numbers. Solve all of them for me. Convert the following numbers to, let me write it. Convert the following numbers to base 2. So okay, so 65, 70, 90, and 99.
Hi, my name's Erica Gomez, and I'm an engineering manager at Amazon.com. One of the best things about working in tech, and at Amazon in particular, is that I get to bring my dog with me to work every day. My job is to help make sure software gets out the door, and her job is to nap under my desk and snore very loudly.
My name is Jerome Holman, and I'm a program manager on Team Xbox, and I have a really fun job, basically bringing the hardware and the software together to give you all the games that you love on your Xbox.
When you look inside a computing device, you see a bunch of circuits, chips, wires, speakers, plugs, and all sorts of other stuff. This is the hardware. But what you don't see is the software. Software is all of the computer programs or code running on this machine. Software can be anything from apps and games to web pages and the data science software that me and my teams use at Amazon to understand how customers behave. But how do the hardware and the software interact with one another? Let's start at looking at a computer's central processing unit, or CPU.
The CPU is the master chip that controls all the other parts of the computer. A CPU needs to do different things, so inside it has smaller, simpler parts that handle specific tasks. It has circuits to do simple math and logic. It has other circuits to send and receive information to and from different parts of the computer. The real magic of the CPU is how it knows which circuits to use and when to use them.
The CPU receives simple commands that tell it which circuit to use to do a specific job. For example, an add command tells the CPU to use its adder circuit to calculate a new number. And then the store command tells the CPU to use a different circuit to save that result into memory. Just like numbers, all of these simple commands can be represented in binary ones and zeros, or on and off electrical signals. The binary commands are stored in memory, and the CPU fetches and executes them in sequence, one after the other. This sequence of commands is in fact a very simple computer program.
Binary code is the most basic form of software, and it controls all the hardware of a computer. These days, nobody writes software in binary. It would take forever. Today, the software we write looks more like this, or even this. Programming languages like these let you type in commands in something that looks a lot like English. To draw a rectangle on the screen, you just need a single command. This high-level command is converted into hundreds or thousands of simpler binary commands that the CPU understands.
Software tells the CPU what to do. But when you're listening to music and browsing the web and chatting with a friend, your computer is running multiple pieces of software all at once. So how do all of these programs get on the computer in the first place? And how can the CPU run them all at once? To find out, we'll have to take a look at the operating system.
The operating system of the computer is the master program that manages how software gets to use the hardware of the computer. For example, I helped create the Windows operating system that runs on most personal computers. The operating system is a program with special abilities that let it control the other software on the computer. It lets you install new programs by loading them into your computer's memory. It decides when a program is run by the central processing unit and whether that program can access the computer's input and output devices. And when you think your computer is running many programs at once, in reality, it's the operating system that's quickly switching between programs, sharing that CPU for fractions of a second.
Inside every computer is an operating system managing software that controls the computer's hardware. The software is a series of commands made of simple binary code, and that binary code is just electrical signals flowing through billions of tiny circuits.
Computers have the potential to do all kinds of amazing things. But the only thing that makes a computer smart or useful is you. When you learn to code, you get to define the problem you want to solve and write the software that turns those ideas into reality. That gives you the power to build things that matter to you, your community, and the world.
All right, so I gave you this question here and I asked you to use a division method to solve it. And you've been able to do that. And from your answers, I can see that the division method is much easier for you. Yes, and you can use a division method to calculate any number. There are a number of other ways you can solve this. And you can also use a calculator, a scientific calculator, to solve it. Because I am using a calculator to check your answer. So once I enter the number, I'll see the answer in binary. All right. Another way you can solve this is by using a table method. Let me show you how the table method is, and then we'll learn how to convert back from binary into decimal, and we'll close for the day. Now, a table method you can use. Are you seeing my screen? All right, so I've drawn a table with 8 columns. I've drawn a table with how many columns? 8 columns. Now, I did this because we are working in base 2. And to work in base 2, that is a table you have to use. When you are working in base 10, you will also use a table. Let me use a table with just 4 columns. In base 10, we call this side. Can you see my table? Can you see my table? In base 10, we call this the ones column. The ones. And we call this the tenths. We call this the hundreds. And we call this the thousands. The thousands. So if you have any number in this column, you refer to it as ones. So if anything is here, it is ones. So if I put number 3 here, this is just 3, right? If I put 3 here, this is in a tens column. So this 3, you not just call it 3, you call it 30. So when you are counting this, you call this 33, because this position is a tens position. If 3 is in the hundreds position, we call it what? 300. So when you are asked to read this, you read it as 333, because the last number is in the ones position. The next number is in the tens position. This number is in the hundreds position, and the number here will be in the what? The thousands. So if I put 1 here, this 1, even though it's 1, it's in the thousands position. So you read it as what? You read it as 1,000. So when you are asked to read a number like this, you read it as 1,333. Is that not how you read it? Excellent. When it comes to binary, we have the binary is in base what? Fix it, okay? Fix it. It's in base 2. So with that one, we have the ones position. Here we have the twos position. We have the fourth position. Fourth, that is fourth. Then we have the eighth position. Then we have the 16th position. We have 1, 2, 4, 8, 16, 32, 64, 100 and what? 28th position. So they are all in positions just like the base 10. So now watch this. If there is a number in this position, it is simply a 1. It's in one's position. Okay, let me just clear the S I put here and give you a simple question, and you see how the answer will appear in a very simple way. Are you with me? Are you very sure? Okay, now you calculate this for me. If you are asked to find the equivalent of number 9 in binary, this is what you do. Binary makes use of just ones and zeros, right? You put 1 in the 8th column and put 1 in the ones column. These ones will have 0, 0. So the code for 9 is 1001, because this is in the 8th position, this is in the ones position. So this is 9. And if you check from what we calculated or converted here, you will see that 9 is just that. Can you see that? Okay. Now, if I ask you to give me number 5 in binary, how will you do it? give me 5 in binary. You put 1 in the first position and put 1 in the ones position. 4 plus 1 is what? So in the middle we have 0. So the answer is 101. Because we have 1 in the first position and 1 in the ones position. That's 5. If you come here and you check number 5, what do you have? Let me give you another number. Let's say you are asked to find 65. Okay, because this is a table, I'll put 1 in the 64th position and I'll put 1 in the ones position. All of this, I'll give them 0. Is that what you got for 65? Those of you who calculated 65, check your answer. Is that what you got? Excellent. Now, let me give you another number to find for me. If I ask you to find, watch this, so find number 13 in binary, how will you do it? 13. I'm going to call someone to do it for me. Right, this is yours. 13. How will you do it? One where? Hey. You put 1 in the 8th position. 1 under 1. That means you have 9. This is 9. You have to find 13. Try again. Right, this is your question. Start again. Your question is find 13 in binary using the position method. How will you do it? 13. You put 1 under 8. One under 4. 1. So your answer is 1101. That's number 13. Let's go and verify from here. 13. What did we get? Is it correct? Okay, good. I'm going to give the next person. Caesar, this is yours. I want you to find number 25. Yes, using the position method. 1 will be under 16. 1 will be under 8. What will be under 4? What will be under 2? What will be under 1? So the answer is 1101. Is that what you got when you calculated 25? When we calculated 25, is that what we got? 11001. Is that what we got? 11001. Okay, so you are right. This method, is it easy or is difficult? It's easy. Okay, next person. Next person will be Millicent. Millicent, your number is 70. 70. How will you calculate 70 using this method? So what will you put under 64? So this is 70. That means 64 plus 4 will be what? 68 plus 2, 70. That means no matter what, you are right. So it's 1000110. Now, when you converted 70 from here, when I give you the assignment, 70, let's use the division method to find 70 together. So we have 70 here, and we have remainder. How many times will 2 go into 70? 35, remainder 0. How many times will 2 go into 35? 17, remainder. How many times will 2 go into 17? 8, remainder. How many times will 2 go into 8? 4, remainder. How many times will 2 go into 4? 2, remainder. How many times will 2 go into 1? Remainder. How many times will 2 go into 1? Remainder. So 70 in binary is written as 1000110. Is that it? 1000110. Is that it? Let's check what Millicent got from here. 1000110. Is it the same? Okay. So the division method and the positions method, which one do you like? Like the division method. All right. You want to ask a question? Yes, always. Always. Yeah, always. We call them most significant digit to the least significant digit. So later we'll learn more about those things. All right. Now, we are going to learn how to convert. Now that you understand how to convert from decimal to binary, I'm sure no matter the answer, the question I give you, you can solve it now. I'm very, very sure. Now, let me add something before we continue. Please, are you with me? We are not done. Because we operate in bytes. Listen to me carefully. Because we operate in bytes, and we said, how many bits will give you 1 byte? Pardon? 8 bits will give you 1 byte. Okay, so now we have told you that 8 bits has been standardized, meaning 8 bits has become a standard in IT or in computing for checking the capacity of or the storage size of data in IT. For checking the storage size of data. Because of that, whenever you are given any calculation to do, you will be asked to leave your answer in 8 bits. Listen carefully. Because 8 bits has become a standard, most of the time, when you are given a question to convert from binary or from decimal to binary, you will be asked to leave your answer in 8 bits. Because 8 bits has become a standard. Now, this answer here, how many bits do you see? I see 7. 1, 2, 3, 4, 5, 6, 7. This is the answer in 7 bits. When they ask me to leave my answer in 8 bits, this is how it's going to be. 70 in 8 bits will be like this. I'll just put 0 in front of it to fill up the space to make it 8. The 0 in front does not change anything. Are you with me? When they write 02, is it not the same as 2? When they write 05, it's the same as 5. When it's 50, then it's not the same. But 0 in front is the same, right? So when I put 0 here, it doesn't change the value. It is still the same. Please, are you here? Let's check this one. How many bits is this answer? How many bits? This answer is in 5 bits. When you're asked to leave your answer in 8 bits, how will you leave your answer? Pardon? 000 11110. Is that it? Exactly. This is 30 in binary in 8 bits. Let's check another one. How many bits is this answer? It's 5 bits. When you are asked to leave your answer in 8 bits, how will you put it? This is exactly what you have to do, because computers operate in chunks of 8 bits. So you should always leave your answer in 8 bits. Now, whenever you are given a strange binary code, let's say you work in intelligence and someone is communicating to some spy somewhere, and the message is this is a message. Only those who can read this message can understand it. So this message has been sent to some secret spies, and you, as an investigative agent, you are supposed to decode this message. How can you decode this message? This is a message. This is a message that can be a word. This can be a word or a command. Later, we'll learn how to convert from binary into text. So when you see this, you can easily change it into text and see what the message is saying. Right now, we are just learning how to convert it into decimal numbers. The reason I put this on the screen is that if you are supposed to interpret such a message like this, all you have to do is to pick it in 8 bits. So I will separate them 8 bits and calculate the first 8 bits. Find the next 8 bits and calculate. Find the next 8 bits and calculate. Because even though the codes are together, they are counted in 8. So I can convert this 8 into decimal. I can convert it into text. Are you with me? Now let's convert this first 8 into decimal. Anytime you are given binary code to convert to decimal, it will be in 8 bits. If it's not in 8 bits, you have to put it in 8 bits first before you calculate it. Now, to convert this code here into decimal, you are going to use this table we used over here all the time. This is a table we use to convert from binary to decimal. Are you with me? So if you don't know this table, you just have to memorize it. Write 1, 2, 4, 8, 16, 32, 64, 128. 1 plus 1 is what? 2 plus 2 is what? 4 plus 4 is what? 8 plus 8. 16 plus 16. 16 plus 16. 32 plus 32. 64 plus 64. Okay. So you do this 8 times because we are operating in 8 bits. Now, whichever code you are given, just feed the code into it. Someone should memorize this code. 01010100. Is that it? You come and feed it from here. 010101. Sorry. 0100. Is that the code? Now, when you are asked to find the answer in decimal, it's going to be 64 plus what? 16 plus what? Plus what? Plus what? Plus 4. That's it, right? So what is it going to be? What's the answer? 84. Now, because you are dealing with binary, it is very easy to know that it's 84. Other number systems also follow their own tables. And so the actual formula for calculating this is this. I'm going to give you the actual formula. To calculate this is what you do. 128 times 0 into bracket plus 64, another bracket, 64 times what is under it times 1 plus into bracket 32 times what is under it plus what? 16 times what is under it plus 8 times what? Plus 4 times what? Plus 2 times what? Plus 1 times what? This is the actual formula. This is what you are supposed to do. Now, what will happen is that in mathematics, anything times 0 is what? So we are going to get 0 plus 64 times 1 is what? Plus 32 times 0 is what? Plus 16 times 1 is what? Plus 8 times 0 is what? Plus 4 times 1 is what? Plus 2 times 0 is what? Plus 1 times 0 is what? Now, you can see that wherever 0 appeared, we got 0. We got 0, didn't we? Wherever we had 0 under, it became 0. So when you see something like this, all you have to do is to ignore the zeros and just focus on the ones, because the zeros will still end up with 0. So we will not bother ourselves working on the 1 to 8 because it will give us 0. We will only focus on the ones and we'll just add them. So 64 plus 16 will give us what? 80 plus 4, 84. That is why when you see anything like this, just forget about where the zeros are and pick where the ones are and add them. That's all. Because if you go and do the calculation, you still end up getting 0. But then you need to know how the calculation is done. Because in other number systems, we are also going to use the same calculation. Because they will also have their tables and we will have a calculation for them. And you have to calculate this way before you get your right answer. This is how to convert from binary to decimal. I just gave you a binary code and I asked you to interpret it in decimal. And you got it for me. The answer was 84. This 84, if I'm supposed to move it into text, I can know what it means in text. Next time we'll do that. Now, your job is to convert this code into binary decimal for me. Convert this code into decimal for me right now. I've given you a binary. Convert it to decimal. Some of you have finished. The code is 10101010. All you have to do is to feed it into this table. This is our magic table. We'll feed every code into it. It's 10101010. So let's just focus on the ones. So we have 128 plus 32 plus 8 plus 2. Let's calculate it. 128 plus 32 will give us what? 160. Is it 160? 160 plus 8 will give us what? 168 plus 2. 1 what? Is that what you got? 170. Now, from today, don't ever forget how to convert binary into decimal. From today, don't ever forget how to convert decimal into binary. Don't ever forget it. Don't ever forget it. Because this will be the key to building upon your knowledge. Later, we'll learn how to convert from binary code into text. And like I told you, the numbers you see here can be a secret message. When they send this secret message to some agents, they know that most people cannot read it. So you can see the message, but I don't know what it means. Only those who can decode it will know what it means. So if you can decode this message, then you can interpret it. When we finish learning this lesson, everyone will be asked to write their names in binary. So your name will look something like this. Only those who can read it will know what your name is. So by the time we finish, it will be very easy for you to write your name in binary code, or when you are given a code like this and you are asked to decode the message, you can decode it. All right. So today we have learned decimal to binary, and we have learned from binary to decimal. So we will end our lesson here. Next time we will continue with binary to what? To text, and it will fascinate you. Thank you for coming. I'll see you in the next one. Bye.